So welcome everybody, my name is Liz Chafin. I'll be presenting the introductory webinar to odor control solutions. It's part one of a 5-part webinar series. Today we're reviewing hydrogen sulfide gas generation and worker health and safety. The next webinar is on nitrate solutions that reduce hydrogen sulfide gas to safe levels and prevent corrosion. Part 3 covers pH sift technology, utilizing liquid phase treatment to prevent hydrogen sulfide gas from even forming. Next would be vapor phase technologies that as an alternative solution to atmospheric odor control using porous media to capture odorous compounds, which will be covered in our air scrubbers webinar. Part 5 of the series will cover oxides and iron salt liquid phase solutions. We encourage everyone to register for all future webinars. So as a quick overview of what we're going to be covering today, we're going to be defining hydrogen sulfide, the health and safety concerns addressed using odor control technology, and answering the question, where does hydrogen sulfide gas come from? When it comes to wastewater odors, there are a lot of compounds that exist naturally in sewage that have a variety of unpleasant smells. There are 3 main categories of odorous compounds found in wastewater: inorganic odors, organic odors, and amine odors. Today, we'll be focusing primarily on odor complaints that occur in municipal water systems from hydrogen sulfide. So hydrogen sulfide gas is an inorganic odor. It's a colorless gas and characterized by having a pungent rotten egg odor. It is much heavier than air, forming in wastewater and capable of escaping from wastewater into air and enclosed air spaces. It is corrosive and must be eliminated from wastewater using chemical dosing equipment, for instance, liquid phase chemical technologies, or by utilizing an active ventilation method to eliminate the gas directly from the air via a vapor phase odor control system. Unlike organic odors, hydrogen sulfide can travel longer distances and affect locations further away from its point of origin. Hydrogen sulfide gas can form plumes thousands of feet long in high enough concentrations and with favorable wind conditions. So why are we concerned about treating this gas specifically? It's because hydrogen sulfide gas is toxic to human beings. Typical ambient air and atmospheric conditions for municipal services job sites fall into the quote-unquote offensive odor concentration range for hydrogen sulfide, but nonetheless, higher unsafe concentrations of hydrogen sulfide are sometimes discovered. Unsafe concentrations can be found inside confined spaces, such as wet wells and manholes, where it's common to deploy sulfide monitors or collect liquid samples. The Occupational Safety and Health Administration, OSHA, specifies limits for hydrogen sulfide exposure due to health and safety concerns. Additionally, OSHA sets a time-weighted exposure limit of 10 ppm time-weighted average during the 8-hour work shift. Quote-unquote, exposures must not exceed 20 parts per million, ceiling, with the following exception: if no other measurable exposure occurs during the 8-hour work shift, exposures may exceed 20 ppm, but no more than 50 ppm peak for a single time period up to 10 minutes. We advise using proper PPE when operating in hydrogen sulfide release areas, including hydrogen sulfide monitoring devices that will alarm when hydrogen sulfide gas is detected. In the table that you can see on this slide, we've identified some of the thresholds that occur at different parts per million concentrations in the air. So from hundreds to tenths of a ppm, 1 ppm, you will detect the rotten egg smell, a lingering odor. And at about 100 ppm, you get a loss of smell. Your olfactory fatigue means your receptors are maxed out, quote unquote. And 10 to 500 ppm, you get various respiratory issues, acute respiratory failure, prolonged exposure can even cause eye injury. 500 to 1,000 ppm is immediately fatal. So not only is it toxic, but it's responsible for infrastructure corrosion within the sewer collection system. The impact of corrosion is one of the biggest driving forces behind what we do in municipal services. We provide products and technologies necessary to protect infrastructure by eliminating hydrogen sulfide and controlling corrosion that occurs in sewers and sewer systems. The corrosion occurs because hydrogen sulfide that is released from the wastewater into the air comes into contact with bacteria. These bacteria, known as thiobacillus, consume the hydrogen sulfide and convert it into sulfuric acid. The acid then causes the corrosion damage, eating through iron, concrete, copper, and other corrosive metals. The force main pipe pictured was corroded along its center line because of the hydrogen sulfide that ate through the ductile iron piping. These sewer pipes are commonly found underneath roads and other above ground structures. Once these pipes begin to leak, sediment and soil can wash away with the sewage. Prolonged exposure to a leak eventually leads to sinkholes and collapses underneath these roads and structures, resulting in serious infrastructure damage. In sewer collection systems, corrosion damage is very commonly observed in iron force mains or concrete structures such as gravity sewers or wet wells. We also see corrosion in copper electrical wiring found inside control panels located at lift stations or wastewater treatment plants. Corrosion can also occur at wastewater treatment plants with other metallic components such as structural members of the plant, gratings and walkways, or even large pieces of equipment such as grit collectors, bar screens, and sludge press conveyor belts. All very expensive equipment. We are going to launch a poll to answer the question, what is your primary concern with hydrogen sulfide? And we will discuss the results of the poll question at the end of the webinar. Perfect. So where does hydrogen sulfide gas come from? The short answer is from a bacteria living in the wastewater. Sewage is a highly active environment rich in organic matter and nutrients that allows bacteria and other microorganisms to thrive. Evoke was primarily concerned with treating hydrogen sulfide, which is the off gas from what's called sulfate-reducing bacteria, or SRBs. To put it simply, these bacteria consume sulfate, then quote-unquote exhale hydrogen sulfide. Common types include Thiobacillus and Beggiatoa. So how does sulfate get into the water supply? If we were to take a sewer pipe and look at a cross-section of it, we often find an area of the pipe's inner wall where bacteria can grow, known as the slime layer. This slime layer is only about 1 millimeter thick and is home to a variety of bacteria and microorganisms commonly found in wastewater. Sulfate-reducing bacteria, SRBs, need oxygen to survive. Force mains are completely filled or fully charged sewer pipes and have a limited supply of oxygen dissolved in the wastewater. As the sewage travels down the pipe, the oxygen is eventually depleted as the bacteria in the slime layer consume oxygen from the wastewater. As the bacteria consume oxygen, they produce carbon dioxide gas, CO2, which is odorless, non-hazardous, and non-corrosive. Once the dissolved oxygen is gone, the bacteria in the slime layer turn into other compounds found in wastewater that contain oxygen and use these to quote-unquote breathe. So after oxygen, the bacteria then consume a compound called nitrate, NO3. Bacteria consume nitrate and produce or expel nitrogen gas, which is also odorless, non-hazardous, and non-corrosive. Unfortunately, nitrate is not overly abundant in wastewater. So after oxygen and nitrate are depleted, the bacteria turn into the next most available oxygen-containing compound in wastewater, sulfate. The bacteria strip off the oxygen atoms of sulfate as part of their respiration process, and the remaining sulfur atoms are converted into hydrogen sulfide and expelled. So as a note, oxygen nitrates are found in organic matter, considered quote-unquote food for both aerobic and anaerobic bacteria. The more food that is consumed, the more oxygen that is used up, and the more food that is used, the more hydrogen sulfide that can be created. So I'm just going to run through a really quick simplified animation of what we just covered. What you see now is the bacteria that is located in the slime layer on the surface of the pipe wall. So the sulfate, which consists of 1 sulfur atom and 4 oxygen atoms, exists dissolved in the wastewater and is consumed by bacteria. Here we go. So the bacteria then removes the oxygen for its respiration and breathing process. So when this occurs, sulfide ions are left behind and expelled back into the wastewater. Depending on how acidic the wastewater is, free hydrogen ions, the H+, will bind with the sulfide to produce hydrogen sulfide gas. The more acidic the wastewater, the more free hydrogen ions there are to produce hydrogen sulfide. And then lastly, we have the hydrogen sulfide gas that is dissolved in the wastewater and can be released into the atmosphere due to turbulence. If there's a lot of agitation in the wastewater, the gas will strip out and escape from the liquid into air. Second, if the temperature of the wastewater is high, there's a greater tendency for hydrogen sulfide to escape. Third, wastewater pH can affect sulfide release. A higher pH value will trap the hydrogen sulfide, but lower pH allows it to easily strip out and escape. So sulfide in solution exists in one of three forms: dissolved hydrogen sulfide gas, bisulfide, and sulfide. Of the three, hydrogen sulfide is volatile and can be liberated through turbulence. You can see in the graphic to the right. The prevailing form depends on, after turbulence, the prevailing form depends on pH. As pH increases, hydrogen sulfide shifts to one of the two non-volatile ionic forms. So as you can see, you have less hydrogen sulfide escaping to atmosphere. So quick wrap up as an aside, we covered hydrogen sulfide gas. That is naturally occurring odor compound produced by sulfide reducing bacteria, or SRBs, in wastewater collection systems. Prolonged exposure to high concentrations of hydrogen sulfide gas can cause significant corrosion damage to municipal sewer infrastructure. This can be disruptive, destructive, and costly to repair. There are numerous health and safety risks associated with hydrogen sulfide gas based on its concentration. Wearing the appropriate PPE monitoring device saves lives. So as a quick aside, our next webinar series will build on what you've learned today on nitrate solutions. We'll be covering calcium nitrate as a solution because it eliminates the odor, corrosion, and safety problems associated with hydrogen sulfide by achieving sewage odor control naturally. So this proven solution also treats other common sewage odors, including odor sulfur compounds such as mercaptans and organic sulfides. So if you have any questions, we're going to spend the next few minutes waiting to see if anybody has questions from the crowd. Anything that we go over today and you still have remaining questions, you can feel free to reach out to me or to the product manager, Calvin Horst, who has been helping me today. And we thank you for your attention.
Maybe while we're waiting for them to roll in, it's a good opportunity to share the results of the poll.
Yes, so 44% have answered for odor control, 11% worker safety, 31% infrastructure corrosion, and 13% customer complaints.
Great. And I should comment that the result of these polls are pretty consistent with what we see in the market as we go about our day-to-day lives of providing odor control services. We do have a couple of questions rolling in. First question, could you provide some guidance on what normal level of hydrogen sulfide would be in a sewer in Parks Pavilion and at what level triggers concerns? So there's a lot of literature out there that kind of dictates what an appropriate level of H2S is in a collection system, and it's largely what we see in practice is largely dependent on the characteristics of the collection system. So when we talk about things like hydraulic retention time, really what we're talking about is the time that the bacteria that exists in the collection system has to start consuming the different oxygen sources. So as Liz mentioned, bacteria will preferentially consume dissolved oxygen in the collection system. And then in the absence of some other source of oxygen, the bacteria will then start consuming the oxygen on the sulfate, which makes hydrogen sulfide. So factors that the primary factor that contributes to the generation of hydrogen sulfide is that retention time and the amount of sulfate that's existing in the wastewater. So if you have an application that, or a portion of your collection system, for example, that has a 1 hour hydraulic retention time, we would expect to see lower hydrogen sulfide concentrations versus a system that's maybe oversized for the flow and has a hydraulic retention time greater than 24 hours. Would expect to see much higher levels. And where we tend to see it more prevalent are long, hot, flat places like Florida. And that's not to say the folks up in the Northeast where it's a bit cooler and a little bit hillier don't have hydrogen sulfide, but you could pop a wet well in Florida and expect that there's going to be some level of hydrogen sulfide there. So in practice, we may see concentrations as high as, well, I guess my experience, the highest I ever saw was about 6,000 ppm. We had to do multiple dilutions just to be able to measure it. And a typical, range that we might see and be asked to take action on would be anywhere from 100 to 500 ppm at a higher range, and then getting lower than that, maybe 30 to 50 would be something that a utility would ask us to treat. As far as what is appropriate, that's really something that is up to the utility. Now, we talked about some of the health concerns that we see, olfactory paralysis starting at 100 parts per million, headaches at 50, nausea at 50 parts per million. So if there's an area that's going to be, that's going to have people around it, workers, and it being exposed to it, then, you'll want to give some consideration to the OSHA requirements for safety. I believe the EPA put out a study some number of years back that said that corrosion is greatly mitigated under 10 parts per million. We've conducted a similar study ourselves and seen similar results. So really what you would want to target depends on the goals of the utility. For odor control, we usually recommend maybe less than 10 or 25 parts per million, but again, it depends on the buffer zone around the emission source. If you have a wet well that backs right up against some community center or homes or something like that, you might want to treat to a lower limit or use some sort of point source odor control like an air scrubber to address odors that are coming out of the wet well. And if you've got a larger buffer zone, you may be able to treat to a higher limit and recognize a little bit more economy with your treatment program. We got another question here, Liz. Does the emphasis on hydrogen sulfide ignore many other odorous compounds? And I'm happy to address that one if you'd like as well. So when we say we're emphasizing hydrogen sulfide, the reason we're doing that is because it's the most prevalent odor that we see in wastewater systems. By treating hydrogen sulfide, we're oftentimes treating a lot of other odorous compounds, but there are things like ammonia, for example, that might follow an opposite relationship with respect to solubility and pH that hydrogen sulfide does. So when we're addressing odor compounds, we're, by nature of the fact that we're doing something, we're addressing all of them, but hydrogen sulfide, I shouldn't say all of them, we're addressing the majority of compounds, but hydrogen sulfide tends to be the most prevalent odor-causing compound and the most, I guess, dangerous in terms of personnel exposure and corrosion. So that's why we target it. It's also quite a bit easier to measure with off-the-shelf, corrosion monitors, odor logs, and the like. We have another question. Can you use a model to predict gas phase hydrogen sulfide based on liquid phase sulfide concentration? I think, Liz, you touched on this a little bit with pH and temperature, but can you expand a little bit on some of the factors that might contribute to the release of hydrogen sulfide that exists in the wastewater, being released to the atmosphere?
Sure. So I guess the way I would start by answering this question is yes, we do have a model. What we typically do is we collect information in the area of the sewer where you're receiving odor complaints. We're noticing high concentrations of hydrogen sulfide. And so we take liquid samples as well as vapor phase samples to use a mathematical model that drives a curve. So based on different kinds of product lines and different feed systems that we have, we model that and then apply into a certain area. So whether or not it's downstream treatment or on-site treatment will depend on what model and what product line and feed system we recommend. I guess what we didn't touch on more so as well, and I mentioned it a little bit, is the amount of BOD in the wastewater also contributes not only to, we talked about turbulence, pH, but the amount of carbon and nutrients in your wastewater also affect what your bacteria will do. And so we try to model that as well and predict how your wastewater will use its nutrients to produce certain amount of hydrogen sulfide gas and then reduce that bacteria. Do you have anything to add, Calvin?
No, I think you covered it well, and that's a good segue into the next question, that and the previous question actually. The question is, not all wastewater odor issues are the same, i.e. different compounds, different conditions that contribute to the release of hydrogen sulfide. How does one go about picking the right solution for any odor control problem? So I guess maybe a good way to narrow that down would be what is the evaluation process that Evoqua goes through? So we had this webinar on general odors. The next one's on nitrate salts, and we move into pH shift, iron salts, vapor phase, etc. What is the process by which Evoqua selects what technology is appropriate for an application?
Of course. Okay. So when designing an odor control application, Evoqua evaluates and values providing transparency and objective compliance. To do this, we first have to understand the goals of the customer. So who is your customer, and what are you trying to do as maybe a municipality for your customer? There's both budgetary concerns as well as hydrogen sulfide levels and what you need to meet for worker safety. And once we've established budget targets and control limits, the most technically efficient and cost-effective solution is selected from a suite of different product solutions. So do you need vapor phase, liquid phase? What kind of liquid phase would you maybe need? What are the constraints in your budget, as well as what are the constraints of on-site solutions? So I think that covers it.
Yeah, thanks, Liz. And the following webinar series, we'll get into specific criteria for selecting different odor control solutions.